This is the 7th video in our series on rings and fields, and we spent the first 6 videos really looking at examples as well as different things that can go on within rings, mostly focusing on factorization. I think that's like a nice intuitive way to start this kind of thing. But we're finally ready to push into some more abstract topics, and that's going to start with the notion of cosets, ideals, and quotients. So let's start with the notion of a coset. So let's say that we're given a subring S of R. So I should point out here that R is any ring at all. It need not be commutative, it need not have an identity or anything like that. So it's any ring at all. Okay, so back to this. So let's say we've got a subring S of R. Then the coset of S with representative A, where A is an element of R, is written like this. So it's A plus S. So we're not really adding A and S. They're different types of things. A is an element and S is a subring. That's just our notation, A plus S. So that's going to be everything of the form little a plus little s, where S ranges through all elements from our subring S. Now, if you know something about ring theory, you might say, well, we don't generally define cosets for any subring. Well, and that's for a very good reason that we'll discuss a little bit later in this video, but we can define cosets for any subring. You just don't get maybe the nice structure that you're thinking of. Okay, so let's maybe look at some examples. So first off, I want to recall that the integers form a ring, and within the integers, you've got maybe a bunch of different types of subrings. Well, really one type of subring, but maybe a bunch of different classes of that subring. And let's think about the subring 3z. So that's going to be all multiples of 3. So we could look at some cosets attached to this subring. So we could look at 0 plus 3z. So that means we're going to take every element of 3z and add 0 to it. Well, notice that that's not going to change any of the elements of 3z. We're still just going to have all multiples of 3. So maybe we would start here in the middle, 0, 3, 6, 9, so on and so forth. But then we got to go back in the other direction as well, minus 3, minus 6, so on and so forth. But let's observe that that's going to be the same thing as 3 plus 3z, because 3 will just maybe jump up where we are in this subring, but we're going to get the same overall set. And furthermore, that's going to be the same thing as 6 plus 3z, which is the same thing as 9 plus 3z, which is the same thing as negative 3 plus 3z. So as you can see, all of these form the same coset, but with just a different representative. Here the representative is 0, over there the representative is 3, 6, 9, or negative 3, depending on exactly which of those we're looking at. Okay, so now let's look at another coset, maybe 1 plus 3z. So that means we're going to take every element of 3z, every multiple of 3, and we're going to add 1 to it. So that means we would have 1, 4, 7, 10, so on and so forth in the positive direction. And then we'll have negative 2, negative 5, so on and so forth in the negative direction. So let's observe that I just added 1 to everything in that list, but of course that list goes on and on and on forever and ever and ever. But now let's observe that there are cosets that are equal to this with different representatives as well. I guess they're the same coset, but this is going to be the same thing as 4 plus 3z and negative 2 plus 3z. So that's going to be different, the same coset, but with a difference representative. Okay, so let's look at one more coset, and that would be 2 plus 3z. So that means we're going to take every element of 3z and we're going to add 2 to it. So starting here in the middle with 0, that's going to give us 2, 5, 8, 11, so on and so forth in the positive direction. That's going to give us negative 1, negative 4, so on and so forth in the negative direction. So notice I just multiplied, or sorry, I added 2 to every multiple of 3. Okay, so there are a bunch of cosets, well, infinitely many cosets that are equal to this with different representatives. So that would be like 5 plus 3z, 8 plus 3z, 11 plus 3z. Those all achieve the same coset. Okay, so let's look at some more examples of cosets for other rings. Okay, so let's say the next ring that we're going to look at is Z3 cross Z3. So this is a 9-element ring, and the 9 elements are simply ordered pairs where each of the entries come from Z3. And then, well, the addition as well as the multiplication is done component-wise. So we've got 0, 0, we have 1, 0, we have 2, 0. We're going to have, let's see, 0, 1, 1, 1, and 2, 1. And then finally 0, 2, 1, 2, and then 2, 2. So those are going to be our 9 elements of this ring. And we could do like some sample calculations if we wanted to. Like for instance, 1, 1 plus 2, 1 is going to be equal to 0, 2. That's because we have 1 plus 2 in the first coordinate, but since we're inside of Z3, that's going to give us 0. And then we have 1 plus 1 in the second coordinate. We could similarly do something like this, 1, 2 times 1, 2. And let's observe there, we get 1, 1. And that's because 1 times 1 is 1, and then 2 times 2 is 4, but inside of Z3, 4 is the same thing as 1. Okay, so now let's take our subring to be the diagonal subring. So in other words, it's going to be the elements 0, 0, 1, 1, and 2, 2. So good, we've got a 3-element subring. And then I'm just going to partition this off a little bit so that we don't get confused about those parts bleeding over. And I just point out up here that we're viewing this as a subring of Z3 cross Z3. Now let's look at some cosets. So let's first look at 0, 0 plus S, but that's just going to be 0, 0, 1, 1, and 2, 2. So that's just going to be our original subring. There's not really anything going on right there. Now let's next maybe look at 1, 0 plus S. So that means we're going to take every element of S. In this case, it's pretty easy because there are only 3 elements from S, and we're going to add 1, 0 to them. So let's see, if we add 1, 0 to 0, 0, we're going to get 1, 0. If we add 1, 0 to 1, 1, we'll get 2, 1. And if we add 1, 0 to 2, 2, we're going to get 3, 2, but 3 is 0, so we're going to get 0, 2. So we got something like that. Then let's look at this. Let's perhaps look at 0, 1 plus S. So we'll add 0, 1 to each of those elements from S. So we're going to get 0, 1 first, we're going to get 1, 2 next, and we're going to get, let's see, 2, 0 last. So now let's observe that among these 3 cosets, we have 9 different elements. We have achieved all the elements of Z3 cross Z3. Now later we'll see that that means that we have all of the cosets, but we don't quite know that yet. So let's calculate a coset with a different representative just to make sure that we get one of those on this list. Let's perhaps look at 2, 1 plus S. Okay, so if we do 2, 1 plus 1 or plus 0, 0, we'll get 2, 1. If we do 2, 1 plus 1, 1, well, we're going to get 3, 2, but 3 is 0, so we'll get 0, 2. And then if we do 2, 1 plus 2, 2, we're going to get 1, 0. I think that's pretty clear. But now let's observe that the order is different, but this is the same coset as 1, 0 plus S. So we see here this phenomenon that we saw before, and that is we've got the same coset with 2 different representatives. In this case, the representative is 2, 1 and 1, 0. All right, so let's look at one more example before we look at some more maybe results and definitions. So next, let's take the subring 048 inside of Z12. That means our addition is modulo 12. So let's start just doing some calculations like we did before. So let's observe 0 plus s is just going to give us s, so that's 048. We have 1 plus s, so we'll add 1 to each of those, so that'll give us 159. We have 2 plus s, so let's see, that's going to give us 2. 2 plus 4 is 6, and then 2 plus 8 is 10. So we get 2, 6, 10. Okay, let's look at another one. So 3 plus s. So 3 plus 0 is 0. 3 plus 4 is 7, and 3 plus 8 is 11. So notice that we haven't had to reduce mod 12 yet. Okay, now let's look at 4 plus s, and we'll see that we're about to start looping around. So 4 plus s is going to give us 4, 8, and then 8 plus 12, which is 0. So observe that that is the same set as 0 plus s. So we see that 4 plus s and 0 plus s are the same. And you can calculate the cosets with the other representatives that are left over, and you'll see that we achieve only the cosets in this list that we've already built. Okay, so let's look at 2 more quick examples before we move on to results. All right, now 2 more quick examples. So let's start with the integers as a subring of the real numbers. And then let's look at the coset attached to the coset representative, the square root of 2. So notice the elements of this coset will be like the square root of 2, 1 plus the square root of 2, 2 plus the square root of 2, negative 1 plus the square root of 2, so on and so forth. Okay, so now let's look at another example, and let's say that S is going to be this following subring. So it's going to be all the matrices of the form A, B, 0, 0, where I read those as the first row first. And that's where A and B are real numbers. And this is a subring of the ring of 2 by 2 matrices. Now let's look at the following coset. So the coset is going to be attached to the matrix 1, 3, negative 2, 5. Okay, so there's our coset, 1, 3, negative 2, 5 plus s. So let's observe that that's going to be everything of the form 1 plus a, 3 plus b, negative 2, 5, as a and b range through all real numbers. So something like that. We can't really make a list here because of the parameterization of our subring. But now I'd like to observe that since a and b are ranging over all real numbers, I can simply replace 1 plus a with a and 3 plus b with b by re-indexing, if you will. So this is going to be the same set as the set containing the matrix a, b, negative 2, 5, as a and b range through all real numbers. But I think it's pretty clear that that's going to be the same as the coset 0, 0, minus 2, 5 plus s. So there we've got 2 representatives for the same coset. Okay, so now that we've looked at a bunch of examples of cosets attached to subrings, let's prove some general results and see where all of this is going to take us. So we observed that often we had the situation where we had a subring S of a ring R, and we had 2 elements of R, A and B, that were not equal, but the cosets attached to A and B were equal. So in other words, A plus S was equal to B plus S. We saw this with a bunch of our examples. So this leads us to the following question, and that is, well, do we have some sort of nice condition for when the coset A plus S is equal to the coset B plus S? And in fact, we do, and here it is. So it's presented as this proposition. We've got A plus S is equal to B plus S if and only if B minus A is an element of S. So it's an if and only if statement. We've got 2 things to prove. So let's start with the forward direction. So let's suppose that A plus S is equal to B plus S. Let's note that B can be written as B plus 0, but B plus 0 is an element of B plus S, an element of the coset B plus S. And that's because 0 is an element of S. So it fits the form of being inside of that coset. But notice that B is an element of B plus S, but that tells us that B is an element of A plus S. Because B plus S and A plus S are the same. But observe, that means that there exists an element S from our subring S such that B is equal to A plus little s. Remember, everything in A plus big S is of the form A plus little s. That's by our definition over here. But now let's observe we can move some things around here, and we see that B minus A is equal to S, which is an element of S. So let's observe that we have done the forward direction. We started with the assumption that A plus S was equal to B plus S, and we ended with B minus A is an element of S. Okay, so forward direction is taken care of. Now let's work with the reverse direction. So let's suppose that B minus A is an element of S. But let's observe that means that B minus A is equal to little s for some little s in big S. But now we can see the following. We can see that little b is equal to little a plus little s, which is an element of the coset A plus S. And we also see that little a is equal to, let's see, b plus negative s, which is an element of b plus s. Okay, so we've got two things going on here, and these are both important for what we're going to do. We've got little b is inside of a plus s, and we've got little a is inside of the coset b plus s. Now we've got all of our parts sorted out, and we want to show that these two cosets are the same. So let's suppose that x is an element of little a plus s. But let's observe, then that means that x is equal to a plus s. I'm going to say prime here because we already used regular s up there. And that's going to be for some s prime inside of s. So that's what it takes to be inside of this coset. But now what I'm going to do is take this little a and rewrite it with the equation that we have right above. So let's observe that that means that x is equal to b plus negative s plus s prime. So again, that's just replacing little a with this b plus minus s. But now I'd like to observe that this minus s plus s prime is an element of capital S. That's because s is a subring, so it's closed under addition. So that means that this x is really written as b plus something in s. In other words, it's an element of the coset b plus s. So now let's see what we've done. We started here with x is in the coset a plus s, and we ended with x is in the coset b plus s. So putting those two things together, we see that the coset a plus s is a subset of the coset b plus s. And then I'm just going to say similarly, this is exactly the same argument. We get the coset b plus s is a subset of the coset a plus s. But then if we've got this double set inclusion or double subset inclusion, that means that those two cosets are the same. So just to finish it all off, those two statements right there will tell us that little a plus s is equal to little b plus s, as needed. Okay, so we sorted out when cosets were the same. Now we're ready to define some operations on these cosets. Okay, so now I'd like to define some operations on cosets. I'm going to define an addition operation as well as a multiplication operation. So let's say we've got a coset a plus s and a coset b plus s. Then we'll define the sum of those two cosets. So we'll write that as a plus s plus b plus s as the coset attached to the sum of the representatives. So a plus b plus s. And the problem with this equation right here is that these pluses are playing different roles. So I'm going to maybe introduce some color coding. So let's maybe erase all of these pluses. And this orange plus that I'm adding in right here is addition inside of the ring R. So notice that A and B are inside of R, and this is the addition of A and B inside of R. Okay, and now this plus that I'm putting in blue is simply the addition symbol that we put inside of the definition of the coset. So A plus S is this coset defined up here. B plus S is the coset defined here with B's. And then A plus B plus S is again the coset we're defining up here, but just with A plus B. And then finally, this addition here that I'm putting in green is the new operation that we're defining. Okay, cool. And now I'd like to observe we can do kind of the same thing with multiplication. So the product of the coset A plus S with B plus S will be defined as the coset where the representative is the product of the original representatives, A times B. And now I'd like to observe that these symbols are playing different roles again. So let's erase all of them and then color code again. So this blue plus is going to play the same role as the blue plus just above, and that is the plus inside of the definition of the coset. So A plus S here, B plus S, A times B plus S. And then this orange times, which we often leave out as just concatenation, this is multiplication inside of the ring, so A times B. And then this green times right here is the multiplication inside of this coset structure, the product of the two cosets. Okay, cool. Now I color coded it, but generally you obviously wouldn't see it as color coded. In practice, you would use context clues to see what each of these symbols means, or these operation symbols means. Okay. So now we're left with the following very, very important question. And that is, do we need any extra conditions on the subring S? So I'll put here on S so that these operations are well defined. And then if these operations are well defined, we kind of immediately have a new ring structure on the set of cosets. We immediately get a new ring structure because all of the other parts of it being a ring kind of come for free. So that would be like the associativity and the distributive rule and all that kind of stuff. So what do I mean by well-defined? Well, let's recall that two cosets can have different representatives. And so we want the addition and the multiplication not to depend on the representative that we have chosen. Okay, so let's start by showing that addition is well defined. So let's say that we are given that A plus S is equal to A prime plus S. So that means we've got a coset with representative A and A prime. And then let's say we're also given that B plus S is equal to B prime plus S. So we've got a second coset where B and B prime are two different representatives for this coset. And now let's look ahead to what we want to show. So we'd like to show that A plus B plus S is equal to A prime plus B prime plus S. And we want to show that because that will tell us that this addition A plus S plus B plus S is equal to this addition A prime plus S plus B prime plus S. In other words, we get the same sum regardless of which coset representative we take. All right, so let's see how we'll go about doing that. So let's observe the following. So let's take this magenta underline and observe that that tells us that A minus A prime is an element of S. And then let's take this blue underline and observe that that tells us that B minus B prime is an element of S. That's by the proposition that we just looked at. Okay, nice. But now what I'd like to do from here is perhaps add these two equations. So we've got two elements of S. If I add two elements of S, I get a new element of S. So I'm not really adding two equations. I'm adding two elements inside of S to give us a new element inside of S. So that's going to give me A plus B minus A prime plus B prime is an element of S. So again, just adding those two elements of S and then maybe grouping them appropriately. But now notice by the proposition that we proved, this tells us that the coset A plus B plus S is equal to the coset A prime plus B prime plus S. But look, that's what we needed to show that our addition is well defined. So if we go up here to our question, it says, do we need any extra conditions on S so that the operations are well defined? Well, in the case of addition, we do not need any new operations. But as we'll see, with multiplication, we do need to include a new operation. Okay, so let's explore what we need for the multiplication to also be well defined. All right, so let's see what it takes for multiplication to be well defined. So let's say we have the same kind of starting point as we had before. So we have the coset A plus S is equal to the coset A prime plus S. And the coset B plus S is the same as the coset B prime plus S. And now let's observe what we want to show. It's going to be a similar like want to show that we had with the addition, but just in this multiplication world. So what we'd like is for A times B plus S to be the same thing as A prime times B prime plus S. And that's because this product of cosets, A plus S times B plus S, would then be equal to the product of cosets A prime plus S times B prime plus S. But we need those two products of cosets to be the same because they're really the same coset, just with different representatives. So importantly here is that this orange thing that I'm underlining is the same thing as this orange coset that I'm underlining. And this purple coset that I'm underlining is the same thing as this purple coset that I'm underlining. So it shouldn't matter what representative we choose, we should get the same result. Okay, so let's see where we can go from here. So let's do the same kind of thing that we did before. So notice that this magenta underline will give us the equation A minus A prime is an element of S. And then this blue underline will give us the equation B minus B prime is an element of S. But now I'm going to do something slightly different than what we did before. Let's observe that these two lead to the following equations. So we've got A is equal to A prime plus little s1 with little s1 is an element of our subring S. And then we've got B is equal to B prime plus little s2, and that's going to be with little s2 an element of S. Okay, nice. Can now be written as A prime plus S1 times B prime plus S2, just with that replacement. But now I'll use the distributive rule to expand that out, keeping in mind that I do not necessarily have commutativity. And that'll give me A prime times B prime. And then plus, let's see, we're going to have S1 times B prime. And then we're going to have A prime times S1. And then we're going to have plus S1 times S2. Okay, nice. But now let's observe the following, and that is what we really want is going to be given by the condition that these two underlined cosets right here are the same. And that is we want A times B minus A prime times B prime to be an element of S. So let's solve this equation that's just above for this maybe expression A times B minus A prime times B prime. And we'll see that we get A times B minus A prime times B prime is equal to S1 times B prime plus A prime times S2 plus S1 times S2. And we want that to be an element of S. So I'll just put here that this is what we want to happen. Okay, nice. But now let's observe that this S1 times S2 is already an element of S. That's because S is a subring, it's closed under multiplication. So that means what we need is this to be an element of S, this S1 times B prime plus A prime times S2. So we need that to be an element of S. Now that may seem like a tall order, but it's really a little bit more obvious if we specialize. So let's look at case number 1, and that case number 1 will be the case when A is equal to A prime. But notice that if A is equal to A prime, then that means that S1 is equal to 0. That's because we have A is equal to A prime plus S1. But then if S1 is equal to 0, then that means that what we need is for A prime times S2 to be an element of S. Then let's look at case 2. And so case 2 will be like in parallel to that. That will be B equals B prime. But notice that if B is equal to B prime, going up here, that means that S2 must be equal to 0 because B is equal to B prime plus S2. But that means in this case, what we need, S1 times B prime is inside of S. So it still maybe seems a little bit intractable, but I think taking these kind of need conditions and summarizing them as follows will make it a little bit more clear. So here's what we really need, and that is for all little a in our ring R and little s in our subring S. And here I'm kind of forgetting my original objects A and S. Okay, so what we really need is for all A in R and S in S, we have A times S is inside of S, and S times A is inside of S. And observe, if we have that condition, then this pink overlined thing is necessarily an element of S, but this pink overlined thing being necessarily an element of S is what stood in the way of this AB minus A prime B prime from being an element of S. Meaning we have found the extra condition that we have to apply to our subring S so that this multiplication is well defined. And recall there was no other condition for addition, so that means that we have the only extra condition, this one down here under the really need, that we need for this well definition of our operations. Okay, so let's summarize that into a new definition over here and see what we can do with it. So everything that we just did motivates the following new definition, and that's the definition of something called an ideal. So a subring I of R is called an ideal if for all little a in R and little I in I, we have I times A and A times I is inside of our ideal I. So there's this absorption property, if you will. So notice it's still a subring, but it just has this new condition. And recall that this new condition was built so that the cosets had these operations that were well defined. And now we're going to get to exactly what that gives us in a bit, but let's look at some definitions of ideals. And so 2z inside of z is an ideal. Recall that 2z is just all even integers. And we can check this pretty easily. So let's take an element a from z, so that's any integer, and let's take an element I from 2 times z. But let's observe that that means that I is equal to 2 times m for some m inside of the integers. Remember, 2z is just every even integer, so we can write that as 2 times m. But now let's note the following, and we only have to check one of these because we have commutative multiplication here, and that is that a times I is equal to a times 2m, but that's going to be 2 times a times m. But that's pretty clearly even, so that's an element of 2z. Now, this is an example of a more general family of ideals, and that is n times z. So n times z is an ideal of z. So that's just going to be all multiples of n. And we can check that almost as quickly. So let's take a and z, and we'll take I inside of n times z. But observe that that means that I is equal to m times n for some m in z. Remember, n times z is all multiples of n. So we wrote I as a multiple of n. And now again, we only have to check one ordering of the multiplication because multiplication is commutative here. A times I is equal to a times mn, but then that's going to be a times m times n, or if you would rather, n times am. Either way you look at it, that's a multiple of n, so that's an nz. So I guess we didn't check that it was a subring. That's fairly straightforward. We just checked that it had the appropriate absorption property, and it does. Okay, so now let's look at this ideal, which is the ideal of 2 by 2 matrices, where not only do you have integer coefficients, but all of the coefficients are multiples of 3. And we're going to show that that is an ideal of M 2 by 2Z. So that's going to be the ring of 2 by 2 matrices where the integers are the entries. Okay, so I think this is pretty straightforward as well. Let's look at the matrix 3A, 3B, 3C, 3D times the matrix X, Y, Z, W. So just to be sure here, this matrix over here on the left is inside of our ideal I, and then this matrix over here on the right is inside of our parent ring, which we called M2 by 2Z, but I'll just shorten that to R. But now let's take the product of something in I and something in R and see what we get. So using standard rules for matrix multiplication, for this first entry, we're going to have 3 times AX plus BZ. Of course, we factored a 3 out. And then here we're going to have 3 and then AY plus BW in that entry. And then down here we're going to have 3 and then CX plus DZ. And then 3 and then CY and then DW. The important thing here is that all of those entries are still multiples of 3, meaning that this is inside of the ideal. And now in this case, you have to check the multiplication in the other order as well, because it is not commutative, but let's not worry about that. I think that's going to be a similar calculation. Okay, so now let's move on to a third example. Let's say we've got the following ideal, and that's going to be the set of all polynomials that are of the form x times p of x, where p of x is another polynomial. So you can think about this as all polynomials where the constant term is 0, because notice that this x multiplier means that there's no constant term. Now we just have to check that this is an ideal. So let's maybe check that this is a subring, just for practice doing that, and then we'll show that it has the absorption property. Okay. So let's take x times p of x and x times q of x inside of I, and let's observe the following. We have x times p of x plus x times q of x is equal to x times p of x plus q of x, using the distributive rule. But notice that that is an element of I as well. So that means that our ideal is closed under addition. So I guess maybe even a little bit more strongly is we could prove that this is closed under subtraction using the same method. And I say that's a little bit more strong because if it's closed under subtraction, it automatically contains the 0 element, as well as inverses. So this is like kind of enough to check that it satisfies all of the addition type properties. Okay, so now let's take a new polynomial, which I'll call f of x inside of q adjoin x. And let's look at the following. We'll look at x times p of x times f of x. But notice that we can resort this as x times p of x times f of x, and observe that that is an element of our ideal. So that means if we take something from the parent ring and something from the ideal and we take their product, we get something in the ideal. But that not only shows us that we have this absorption property, but specializing this to the case when f is in the ideal also shows that this is closed under multiplication. So in fact, when you're checking that something is an ideal, checking the absorption property automatically shows you that it's closed under multiplication. So you don't have to check that. So any way you look at it, we have shown that this is an ideal. Okay, so now let's move on to a new definition, which is the structure built out of those operations that we saw before applied to our set of cosets. All right, so everything we've done so far has been building up to the following definition. So let's say we've got any ring R and an ideal I of R, then we're going to define this thing called the quotient ring. And that's going to be the set of cosets of I. And we write that as this little r with a slash I. And we read that as R mod I. So again, it's the set of all cosets, so it's the set of everything of the form A plus I, where A is an element of R. So now we'll endow that with the structure of a ring via those operations that we talked about before. So we've got A plus I plus B plus I is A plus B plus I. So that's the addition on this quotient ring. And then A plus I times B plus I is AB plus I. So that's the multiplication on this quotient ring. And again, we know that those two operations are well defined because of this condition up here on the ideal that we really derived the need for that earlier. And you might say, well, there are other conditions of a ring, like the addition is commutative, there's a zero element. Let's see, the addition is associative, the multiplication is associative, there's some distributive rules, so on and so forth, where all of those are actually quickly inherited from the structure on the original ring. So I'll leave it to you to check all of those details on your own. Okay, so now let's look at some examples of quotient rings and then some calculations within quotient rings. So let's start with 4z as a subset of z, or actually an ideal of z. So we checked that nz, where n was any integer, was an ideal. So this is an example of that. So let's look at z mod 4z. So that's the quotient ring. And notice that it's going to have the following elements: 0 plus 4z, 1 plus 4z, 2 plus 4z, and 3 plus 4z. We actually only need those elements because any other element will give us the same coset. And that's by that proposition when cosets were equal. Now we could write out some elements in this if we wanted to, like this would be like -8, -4, 0, 4, 8, so on and so forth. This one down here would be like 1, 5, 9, and then let's see, -3, -7, so on and so forth. This 2 plus 4z would be like -2, 2, and then let's see, 6 in that direction, and then -6 in that direction, so on and so forth. And then this 3 plus 4z would give us like 3, 7, 11 in the positive direction, and then -1, -5, so on and so forth in the negative direction. So that would be writing out some elements of these cosets. So now let's make an addition table as well as a multiplication table and see if we can understand the structure of what's going on here. So here we'll have 0 plus 4z, 1 plus 4z, 2 plus 4z, and 3 plus 4z. So those are all of our elements. And then here we'll have 0 plus 4z, 1 plus 4z down this column, 2 plus 4z, and 3 plus 4z. Now let's do some calculations to see if we can get an idea for the additive structure of this quotient ring. So this shouldn't be that big of a headache. Okay. So using our operations over here, notice that 0 plus 4z plus 0 plus 4z, well, that's 0 plus 0 plus 4z, or 4z. Likewise, this is 1 plus 4z, here we have 2 plus 4z, here we have 3 plus 4z, because we have just 0 plus all of those. Now, furthermore, everything happening below this diagonal is going to be equivalent to what's happening above the diagonal because we have commutativity. So I'm just going to focus on what's happening above the diagonal. Okay, so now 1 plus 4z plus 1 plus 4z, so that's going to be 2 plus 4z. This one's going to be 3 plus 4z. And then 1 plus 4z plus 3 plus 4z is going to be 4 plus 4z. But notice that 4 is an element of 4z, so that just gives us 0 plus 4z. Okay, nice. And then 2 plus 2 is 4, which is 0 plus 4z. And then 2 plus 3 is 5, which is 1 plus 4z. And then 3 plus 3 is 6, which is 2 plus 4z. Okay, so that's the full addition table. And now, well, let's maybe highlight one of these just so that we're all on the same page. Let's maybe underline this in magenta and we'll bring this up here. And let's observe that 2 plus 4z plus 3 plus 4z is equal to 5 plus 4z, but that's equal to 1 plus 4z because 5 minus 1 is equal to 4, which is an element of 4z. Here we're using that proposition that tells us when cosets are the same. Remember, cosets are the same when the difference of the representatives is an element of the subring, or in this case, the ideal. So 5 plus 4z and 1 plus 4z are the same because 5 minus 1 is equal to 4, which is an element of 4z. Okay, so now let's do a similar table, but for multiplication. So let's get that laid out over here. Okay, so there's our multiplication table. So I've started filling it in, but I've got the same 0 plus 4z up to 3 plus 4z up top and over there on the left. And now what I'm doing is I'm taking the product of these cosets in the interior. So notice the product with the coset 0 plus 4z is always going to give us 0 plus 4z because 0 times anything is 0. I don't think that really needs to be discussed. Then the product of 1 plus 4z with anything is going to give us, well, what we started with, because 1 is the multiplicative identity of our ring Z. So let's look at the ones that are a little bit more interesting, and that is 2 plus 4z and 3 plus 4z. And notice that I have left out what's going on below the diagonal because, again, this is commutative, so it's the same thing as what's going on above. So 2 plus 4z times 2 plus 4z is going to be 4 plus 4z, but that's 0 plus 4z. Again, using a similar argument to this right here, that's because 4 minus 0 is equal to 4, which is an element of 4z. Okay, so now 2 times 3 is 6, but then 6 plus 4z is the same thing as 2 plus 4z. That's because 6 minus 2 is equal to 4, which is an element of 4z. Okay. Then we've got 1 left over, so there's 3 times 3 is 9, but 9 is the same thing as 1 because, let's see, 9 minus 1 is 8, which is an element of 4z. So let's maybe look at that one a little bit more carefully just so that we're all on the same page. So let's bring that up here, and let's observe we have 3 plus 4z times 3 plus 4z is equal to 9 plus 4z, but I claim that that's the same thing as 1 plus 4z, and that is because 9 minus 1 is equal to 8, which is a multiple of 4, so it's an element of 4z. Recall that cosets were the same when the difference was an element of the ideal. The difference of the representatives was an element of the ideal. Okay. So there's an in-depth example, or our first example of calculations within a quotient ring. Now let's look at a couple more. So let's look at another example. Let's suppose we've got the ideal containing 0, 3, 6, 9, 12 as an ideal of Z15. So you can check that this is an ideal of Z15 maybe via the definition of an ideal just by taking every element of Z15, multiplying it into these, and observing that you get another one of these. So I'm not going to do those steps, but it should be pretty straightforward. So now what I'd like to do is look at Z15 mod this ideal, so that quotient ring. So let's observe that we've got 3 cosets. We have 0 plus I, so that's 0, 3, 6, 9, 12. We'll have 1 plus I, which is going to be 1, 4, 7, 10, 13. And then we'll have finally 2 plus I, which is equal to 2, 5, 8, 11, and 14. And then I'll leave it to you, but you can pretty easily check that 3 plus I is going to be the same thing as I, and so on and so forth. So now, just like before, we could build an addition and a multiplication table, but let's maybe not worry about making the tables. Let's just do some examples. So let's observe that if we do 1 plus I plus 2 plus I, we're going to get 3 plus I, but let's observe that 3 plus I is the same thing as 0 plus I. And that's because 3 minus 0 is an element of I. Recall that that's what it takes for these cosets to be the same. So here we have 1 plus I and 2 plus I are additive inverses inside of this quotient ring. Then I guess we could do one more. Let's maybe do 2 plus I times 2 plus I. Let's observe that that's going to give us 2 times 2 plus I. In other words, it's going to give us 4 plus I. But I'm going to claim that that's the same thing as 1 plus I, and that's because 4 minus 1 is equal to 3, which is an element of the ideal. Again, we're using that proposition that tells us when cosets are the same. So this means that 2 plus I is its own multiplicative inverse inside of this quotient ring. In fact, I think you could probably argue that 1 plus I times 1 plus I is equal to 1 plus I, meaning that 1 plus I is also its multiplicative inverse. But what that shows us is that everything that is non-zero, we have two elements that are non-zero. So everything that is non-zero is in fact invertible. So that makes this thing actually a field, which I think is pretty interesting also. Okay, so let's look at one more example of a quotient ring, this time built out of a matrix ring, and then I'll leave you with some exercises. So let's recall that before we had this ideal of 2 by 2 matrices with all even entries, and that was an ideal of the ring of 2 by 2 matrices with all integer entries. So we checked that that was an ideal. Now what I'd like to do is claim that if we look at the quotient ring, so that's going to be m2 by 2z mod I, we in fact only get 16 different cosets, which is pretty interesting because notice that our parent ring is infinite and, well, our ideal is also infinite, but somehow this simplifies this thing down to have 16 different cosets. And we can actually describe them very carefully. They're of the form x, y, z, w plus I. So remember, a coset has to be of that form again. But here, x, y, z, and w only come from the set containing 0, 1. Okay, so let's see how the proof of this will go, although it's pretty straightforward. Okay, so let's maybe take a matrix, which we'll call A, B, C, D, inside of m2 by 2z, and then we'll look at its coset. So we've got A, B, C, D plus I. So that's the coset containing, or the coset connected to this matrix. So now what I'm going to do is perform division of A, B, C, and D by 2, and we'll keep the remainder. So that means that I can write this as maybe 2 times r plus x, and then 2 times s plus y, 2 times t plus z, and then 2 times u plus, let's see, what do we need left? W. And this is plus I with, well, we have r, s, t, u are just any integers. And then we've got x, y, z, and w are from our set containing 0 and 1. So again, what I did there is I just performed division with remainder. So I divided a by 2, and I got a quotient of r and a remainder of x. Notice that if we're dividing by 2, the possible remainders are either 0 or 1. But now what we can do is rewrite this, or I claim that this is equal to the coset x, y, z, w plus I. And that's because if we look at 2r plus x, 2s plus y, 2t plus z, and 2u plus w minus x, y, z, w, we simply get the matrix 2r, 2s, 2t, 2u, which is an element of the ideal. But let's recall again that cosets are equal when, if you take the difference of their representatives, you get something inside of the ideal. Now we can do a little example calculation here as well. Let's maybe take the matrix 1, 1, 0, 1 plus I and multiply it to the matrix maybe 1, 1, 1, 1 plus I. So we're multiplying those two cosets. Okay, so let's perform a matrix multiplication. So let's see, that's going to give us a 2 in this entry, another 2 in this entry, and then let's see, a 1 and a 1 in those lower entries. So that's what we get from taking the product of those two cosets inside of our quotient ring. But now let's observe that this coset is equal to the coset 0, 0, 1, 1 plus I, because if we perform division with remainder, we get a remainder of 0 for the two entries in the top row, and we get a remainder of 1 with the two entries in the bottom row. Okay, so now I'm going to leave you with some exercises. Here's some nice exercises. The first is to show that the only ideals of a field F are the whole field and then just the 0 element. So next, let's show that if I and j are ideals, then so is the intersection of I and j and the sum of I and j. Let's just note that the sum of I and j, I plus j, is going to be the set of everything of the form little I plus little j, where little I is in the ideal I and little j is in the ideal j. So next up, let's show that this set, which is everything of the form a plus 2bi, where a and b are integers, is a subring of the Gaussian integers, but not an ideal of the Gaussian integers. And now one last problem, but we're going to use some notational convenience. So over here in this purple box, I'd like to point out that we're going to take R to be a commutative ring. So I didn't write that here, but this is R is a commutative ring. Then we'll say that A times R, where A is an element of R, is going to be all multiples of A. So observe that that's just A times R, where R runs through over all elements of the ring R. And we'll look at things like this next time, but if you want to show that this is an ideal on your own, I think that's probably a good idea. So now let's look at this fourth problem. Let's find all the elements of the following quotient rings and make addition and multiplication tables. So the first is z mod 3z. So notice that this 3z uses that notation that we have over there generalized. The next is z3 adjoin x mod x times z3 adjoin x. So that's going to be all polynomials where the constant term is 0. Notice it's just all polynomials times x. And then next is z adjoin I mod 5 times z adjoin I. So that's the ideal here is going to be all elements of the Gaussian integers where the real part and the imaginary part are both divisible by 5. And then next up is z adjoin I mod 2 plus I times z adjoin I. So observe that 2 plus I times z adjoin I, that's going to be every multiple of 2 plus I inside of the Gaussian integers. So all of these will be fairly small finite quotient rings. Well, it's not totally obvious that these two at the bottom are finite because the parent rings aren't finite, but when you perform the quotient, you do get something finite in all of these cases. And that's a good place to stop.